So 2.2, day 1, we're going to talk about polynomial graphs today. All right, here we go. So we're going to be looking at polynomials. And remember, just for clarification, a monomial is one term. A polynomial is monomials added and subtracted together. So y'all are not going to have any square roots in polynomials. You're not going to have any fractions, any x's below the denominator, just nice, clean, whole terms like what you do on your factor drill. Okay, and y'all, polynomials get pretty high in degrees, but they all behave 3 ways, and we are going to talk about those 3 ways by 3 little baby graphs. I'm going to draw 3 baby graphs here, pretty small. All right, so specifically really just going to talk about what happens when these graphs cross the x-axis. All right, y equals x squared, and y equals x to the 3rd power. Y'all, we know what y equals x is. It's just a straight line. Now look, here's what I want to talk about. When it passes through the x-axis, it starts down here, it passes the x-axis, it goes straight through. Straight, no curves. The only graphs that you graph that are straight are lines. So this is called linear behavior. It passes straight through, no craziness. There's a little bit of craziness here because y'all know what parabolas do. Once it touches that x-axis, it bounces off and goes back in the direction it came from. So it's not straight through, it bounces. But y'all, that's called tangent. It's tangent to the x-axis. It bounces off it at one point. And then the cubic function, the party animal, when it gets around the x-axis, it has so much fun, it creates a little swirl. That little swirl is always going to happen when it approaches the x-axis. And y'all, that swirl, the formal name for the swirl is called change in concavity. So polynomials, y'all, we're going to look at high degrees, like something to the 12th power, something to the 13th power. And when you get a high degree like that, they're all going to have behavior like this. It's never going to be anything different than one of these 3. So let's talk a moment about some little baby examples here. I'll put example 1 on that side. I'll put example 2 over here. Example 1 is going to be f of x equals x to the 5th plus 6. Over here, we're going to have a leading negative. This is going to be negative x to the 4th minus 1. Ooh, let me move this up. Let's see. So what we're going to do is we're going to draw a couple of little baby graphs again. We're just going to get comfortable with these transformations of these polynomials. Our main focus today is going to be analyzing So this is the only time that we're graphing today. We're just graphing these two, and then that's it. We're moving on. All right. So that x to the 5th, y'all, it's going to behave just like this. If it's odd, boom, it's going to behave like that. So, bless you, I need to draw a swirl. There is a swirl that's happening, but you have a K value of 6. So when I draw my swirl, remember it's a sketch, it just needs to be somewhere above the origin because of the plus 6. So that's what this graph is going to behave like. Now remember, it's just a sketch. This graph could go on forever. I don't know what it looks like beyond these, but I know it's up on the right because this is positive. I know it's opposite behavior because it's an odd exponent. And I know that little swirl, that change in concavity, is 6 places above the origin. All right, next one. So for this next one, guys, I am going to graph it in red. I kind of like graphing all the negatives in red just so you recognize they're negative. So this one, y'all, is going to behave like this. We're just going to have a bounce. But the bounce has been shifted one place below the origin. So this graph is going to look like this. And that's it. We're just transforming. Any questions on that? All right, so now what we got, guys, is we've got some, thank you, Mickey, for doing that. I got this much space. That's going to be enough space for what I need to talk about. I need to talk about everything that equations provide us. So we're shifting from graphs. We're going to look at some equations. So here's what polynomial equations provide us. I'm going to make a little graphic. All right, first of all, let me zoom in on this. Hold on just a moment, guys. Let me maximize my space. Okay, all right, so here's what they provide us. First of all, the leading coefficient is the number in front of the highest exponent. It is always the number of the highest exponent. Now remember, if it's negative, negative coefficients are down on the right. Positive leading coefficients are up on the right. So right off the bat, there is a lot of stuff that it provides us. And then we can tell the number of turns that the graph actually makes when it changes from a max to a min. It's called turning points. And turning points are so easy to find because it's degree minus 1. That's all it is. The highest degree minus 1. Polynomial equations also tell us the zeros. And the zeros equal the degree. Don't add or subtract anything. Just take the highest degree, and that's the number of zeros. And then I'm going talk a minute about the word zeros. Y'all, zeros could be x-intercepts. They could also be imaginary. They are numbers that you put into the equation to get an answer of 0. Look, I'm going to go back up here for a moment. Remember when we graphed this? Y'all, does this cross the x-axis? Is that ever going to cross the x-axis? No. But there are 4 answers. They're all imaginary, but there's 4 numbers that I could put into this equation that's going to give me a 0 answer. So zeros is a blanket term for real x-intercepts and imaginary answers. So that's what zeros are. Okay, back to this. Leading coefficient, turning points, degree, and I forgot what I was writing here. Maybe degree? In behavior. Sorry, in behavior. Now remember, if the degree is odd, you're going to have opposite in behavior. If the degree is even, you're going to have the same in behavior. No, I'm sorry. This phone is going on. In airplane mode, I apologize about that. All right. So polynomial equations provide us a bunch of stuff. But now we need to talk about what kind of forms polynomials have.